We are now going to get a little bit deeper into the topic of general purpose input output in a microcontroller. So in order to understand what GPIOs are, let's think a little bit about the context within which a CPU works. Now in what follows, I will be using a couple of terms sort of interchangeably throughout the rest of the sessions that we'll be going through. The CPU stands for the central processing unit, an MCU stands for a microcontroller unit. In a lot of cases, I'll be using the terms interchangeably, and in a lot of cases that difference really doesn't matter, right? So what you need to keep in mind is, at the end of the day, the CPU is the part that is actually running the instructions. The microcontroller unit possibly also has certain other peripherals and so on associated with it. So when we talk about an actual physical system, it would probably be an MCU, but the core part that's actually doing the work is the CPU part of the MCU. So the words are being used sort of interchangeably in some cases, at least over here. Now at its very core, what a CPU has is an ALU, an arithmetic and logic unit, a certain set of registers that store data, and some control logic that actually tells it how to behave, right? And how we decide how it behaves is based on, of course, instructions that are provided by storing somewhere in memory and then reading them out one by one and then passing them to the control to tell the CPU what to do. Now the registers are used for storing the data that is being used for internal computations, but as such this CPU doesn't have any notion of an outside world. It can only work with what are already there in its registers and based on whatever instructions it sees. So what we do is we basically supplement this with memory, right, that allows us to store data, right? Whatever doesn't fit in the registers can be stored here, or whatever is required from somewhere else can be brought in from memory into registers. How do we do that? We use what's called an address, which is a set of wires that basically have maybe some number of pins, right? Depending on the number of memory locations out here, there would be some suitable number of pins that are given as address. They basically constitute a number that tells us some index into this particular set of locations from which I need to either read data or into which I need to write data. First, let's look at how I write data into the outside world. Along with the address, I would give out another set of data which I am calling D out over here, and I would also give out one more signal which is just one wire having a logical value 1, let's say, which basically tells this memory block that I am trying to write something to it. So what does it do? It basically takes the data on D out, it goes to the location marked by this address and changes the value, right, because the write enable is high, to whatever was there in D out. Okay. So we give it an address, we give it data, and we set a control signal to enable writing into a particular memory location. The next thing we could do is we could read. What if I give that same address corresponding to the same memory location out here, and now I give some other signal which is somehow indicating a read? What that memory should do is take the data from that particular location and give it to us on this set of wires called D in. What can my CPU do with it? Take those set of values and put them somewhere into a register out here and then continue processing. In other words, the memory can basically give me back whatever data I had written into it at some previous point, or possibly that somebody else wrote in from this side. I would be able to read that value back through the DN over here. So far so good. This is our interface with memory, right? But that still only allows us to sort of read and write memory locations. Now where this gets interesting is, of course, we first need to think of the bus, right? The term bus is the set of wires that connects the CPU to memory. And as you can see, there are two types of, or two sort of functionalities associated with the bus. One is to carry just data, and the other is control, which is either the write enable, read enable type of signal, or the address itself, right? The D out and D in I am logically treating as two separate sets of wires. Occasionally they might actually end up physically being the same wires, but logically they are two separate things, so we keep them that way over here. So the bus itself refers to all of these signals in some sense, right, which allows us to communicate with the memory. Now here's the interesting thing. I could just as well have taken out that word memory and replaced it with a mystery electronic circuit, right? And the CPU would not be able to tell the difference, right? As long as it gives out an address, it gives out a control signal out here, and it either allows it to write data or rather it just takes the data that it writes, or it gives back data when requested, right? There is no way that the CPU can actually physically tell that this is not a memory block and is some other mystery circuit out here, right? Because there is an abstraction at this point. Now, why is that good news? I mean, why would I want to put in a mystery circuit over there? The point is that I could then replace this circuit with something that basically says, okay, if I write something over here, I don't necessarily need to store it. I just need to know what to do with it. Okay. And similarly, if the CPU asks me what was present at this particular memory location, I can reply with anything I want and fool the CPU into thinking that this was actually something present in a memory location, and the CPU is just going to go ahead and do its work. Okay. So, this abstraction basically allows us to say that I now have a CPU, it has a bus, and it is talking to some set of addresses. That is all that the CPU knows. It can give out an address and it can either try to write something there or read something back from it, right. Now, that set of addresses is what we call the memory map of the system, right. There will be some extra electronic circuitry out here which is usually called the decoding circuitry. And what this decoding circuitry does is, it actually is just a sort of piece of digital circuitry. You have probably come across decoders and multiplexers in the digital systems course, right. All that it does is, you can then say, okay, depending on a certain set of addresses, it will activate this memory block 1, which means that any writes will be sent into memory block 1, any read will come back from memory block 1. If it is from a different set of addresses, I will send it to memory block 2 instead. And if it is yet another set of addresses, I will send it to some other circuit which is actually performing something completely unrelated to memory. It is an I/O, it is an input output kind of circuit. Okay. So, this abstraction basically allows us to sort of take a memory map which is just a set of addresses that we have and split it up and say part of those addresses correspond to one memory block, part of those correspond to another memory block, part of them may correspond to yet another memory block, and other parts correspond to, let us say, different I/O blocks, right. So, what is an I/O block? It is some circuitry which is able to respond when it gets signals from a bus. Either it takes the D out that is being sent in from that bus and does something with it, or if read enable was active, it gives back data that needs to be sent back on D in. As long as it behaves that way, the CPU cannot tell the difference between this I/O block and this memory block. It just treats both of them the same, and the same instructions which are used to store data into memory or to load data from memory can be used to communicate with this I/O block. Okay. Now, with that background, right, we know that this is the picture that we used for our Nucleo board, right, but in that board, this small black square that you see in the middle is the actual microcontroller that is doing all the work that we want, or rather that is running our programs. So, what does this microcontroller do? It has a number of pins associated with it. You can see that there are a bunch of pins out here marked power, in fact, right, which seem to show that yes, there is a 3V3 which actually stands for 3.3 volts. There is another 5V which is 5 volts. There are two pins for ground, GND, which is ground is usually abbreviated as GND. Vn is probably a negative supply voltage for or I am not entirely sure what actually Vn is, so we will leave that aside for now. There is also an AVDD which is the analog VDD, which is used, we will talk about it a bit more when we get to A to D conversion, analog to digital conversion. There is yet another ground signal that you can see on this side, but that is just for convenience, right. It is more so that you have a pin out here that you can use if necessary. So, you can see that these are all a set of power and ground signals that are present out here. Then there are a few pins which are what are called the dedicated communication pins. In this case, there are some pins out here that are not even routed to this part, but go directly, let's say, to the USB chip or something like that, which could be used as dedicated pins just for communication or maybe certain kinds of configuration. But where things get interesting is the rest of these pins, right? All this D7, D6, D5, D4 and so on, all of them are in some sense what are called general purpose I/O pins, input output pins. Some of them have extra capabilities. They can also be treated as analog pins, as you can see over here, right? The A0, A1, A2 and so on. Others are basically meant for use as digital pins, but you can also see that they seem to have multiple functionalities. You can either treat it as SCL, SDA, which we will learn about later when we talk about the SPI protocol, right? Or they can be configured as D15, D14, which means that they are general purpose IOs. So what are these general purpose IOs? As we saw, they are some way by which I can communicate with the outside world. They basically allow me to have something coming out from my CPU, which can go into some register out here. That register is in turn physically connected to one of these pins. So if a bit in that register is set to 1, it would basically cause the corresponding pin to go to the high voltage value. And if that bit is set to 0, it would make that corresponding pin go to the value ground. So GPIOs in that sense are versatile IO pins. They can be configured in different ways, right? And they are used for multiple things, interfacing primarily, right? And they can be used to interface with devices, sensors. A sensor could be something like a push button, something as simple as a push button, or it might be more complicated. It might be a temperature sensor, a carbon dioxide sensor, humidity, right? Various kinds of things of that sort. Although not all of them would be connected to GPIOs, you would probably need some other kind of protocol, but you could even potentially do it using GPIOs. Primarily, they are used in order to detect digital signals. Is something a 0 or a 1, right? They can also be used as actuators, which means that the value written into the GPIO as an output now could be used in order to, for example, turn on an LED, with this example that we already saw. Now the interesting thing and what makes them particularly versatile is this behavior is configurable. You can in fact even take a particular pin and change it from being an input to an output as part of the runtime of the system. Right? And as far as the CPU is concerned, the values that are there in the GPIO pins are seen as bits in a register. And what is a register? It basically is a corresponding memory location, an address from which I can read data and thereby find out what the values of different pins are. Similarly, I can write to that address a register, and that would cause certain changes in the actual physical voltages that are present on those pins. Right? So the programming interface is done through the register or the memory map. The physical interface is actually done through all the electronic circuitry that allows us to make all of these connections for us. So there are a number of important things that you need to understand in the context of how GPIOs are actually used, right? And some of them are not purely about programming, they are about the underlying electronics. And this is something that often gets missed out when people who have approached microcontrollers purely from a programming point of view face difficulties with regarding certain kinds of programming. So it's important to sort of keep these different aspects of the microcontroller in mind as you build upon it. Now one of them is when a GPIO is configured as an output, what's actually happening is that the CPU is driving the pin. What do I mean by driving? It means that this particular thing is connected to a 1 or a 0 depending on a value which is being sent from the CPU. Now driving actually means that this is actually connected to a high voltage supply or it is connected to ground, right? Which means that if this wire was also being pulled up to ground or pulled up to VDD or pulled down to ground by some other circuit, that would be a problem. It would basically cause some kind of a short circuit which can potentially cause a high current to flow and potentially even burn a chip. What is done in practice is I usually have some kind of a buffer a circuit which makes sure that what is coming in on this side is then able to be driven out comfortably on the other side. So this buffer then takes over the responsibility of actually delivering current to this side. Okay, so that's the CPU driving a pin. On the input side, the external world is driving the pin. So this particular pin is assuming that there is data or there is a signal, there is some voltage which is attached from here to this buffer, and that buffer in turn is going to control the voltage on this particular wire, the physical wire, right. And you need to be very careful with these buffers to make sure that you do not try to drive something from the CPU and from the outside world at the same time, especially if you try driving them to opposite values. Let's say you take this up to VDD and the outside world is trying to drive it down to ground. It basically means you are creating a short circuit, a wire that's basically connecting up some high voltage to a low voltage. A large amount of current will try to flow through the system, most likely causing overheating and potentially damaging the circuit, right. So this is something to be avoided. You don't want such a thing to happen. You need to be very clear about which mode you are configuring your system in. In particular, what it means is that if you have a CPU where you are connecting some outside circuit that's trying to drive your system, right, and at the same time your CPU also tries to drive the system, that's when you can really get into trouble and create a short circuit. So your modes have to be set correctly. You need to make sure that if something is connected to an external, a sensor from which you are getting data, your CPU should not also try to drive it, which is incidentally also why by default when the system turns on, all pins are pretty much configured as inputs, right. So that way if you do happen to connect a sensor out here and it's trying to push current in here, that's fine. The CPU will just try and take that current, accept it. It may not actually read it, but it at least gives you time to make sure that all of your connections have been done properly before you start configuring something as an output and trying to drive current out of it. The mode selection can be done using a value, right, which you can basically write into a particular address location or a register location, right. These are all called the registers of the CPU. They are not the same as the registers used for computation. They are actually registers used for setting various mode parameters. And what this particular pin allows us to do is that we can isolate the driving circuit in order to prevent short circuits, right. Basically what we can do is we can make sure that at any point over here, either the CPU or the outside world are allowed to drive onto this particular signal, and they are not going to cause a short circuit by both trying to drive a wire. What that also means is that you should always be careful to explicitly configure pins as inputs or outputs before using them. The normal default would be that it gets configured as an input, that's just for safety. If you want to actually make a pin toggle or something like that, you need to explicitly configure it as an output. But be very careful that you only configure those pins as outputs that actually need values driven onto them, because even by accident if some other voltage tries to connect to a pin that has been configured as an output, you could potentially damage your microcontroller. Now one other thing which an aspect of these pins is that in some cases you even have things that can sort of switch between analog and digital modes. There are others where just the location of the pin pretty much decides whether it's analog or digital. There are certain pins that could be configured to behave either as analog or digital. Now what does analog mean? Analog basically refers to real world signals. Those are actual voltages, right, which can take arbitrary values. For example, if I have a 3.3 volt supply, pretty much any value between 0 and 3.3 volts can come as a result of that supply, right. Values outside that range are not likely to normally happen unless there was some other kind of a temporary waveform that caused a rise in the voltage at some place. But values between 0 to 3.3 volts are naturally present as part of the system itself. On the other hand, digital signals logically represent either a 0 or a 1. Physically, a 0 would usually be the 0 volt or ground, and 1 would usually be the VDD, the digital supply voltage, right. Now what happens to a value like 2 volts, right? And the way that that is handled is digital pins or digital circuits usually have a notion of something called a threshold, where they decide that, let's say it could be that something above 1.65 volts, which is half of the supply, is going to be treated as a logical 1, anything below that would be treated as logical 0. The point is, this is not guaranteed. Your threshold may not be 1.65 volts, it could be 2 volts, it could be 3 volts, right? Because logically the system is basically saying that if you have a 1, it should actually be 3.3 volts. If it's something less than 3.3, you need to figure out what your thresholds are and make sure that they are close enough so that it actually gets treated as a 1 or a 0. So there's no guarantee of what exactly thresholds will be, unless of course the data sheet specifies something specifically, right? And the bottom line is that digital signals are not expected to take on intermediate values for any prolonged period of time. They are expected to quickly settle to either ground or VDD as quickly as possible. Now analog signals on the other hand are expected to be somewhere in the middle of that range, and the way that we deal with them is we use something called analog to digital conversion, right, which is usually present in most microcontrollers. Not all of them are guaranteed to have analog to digital conversion capabilities, but most of them do have at least some basic capabilities. What it allows us to do is to interface with sensors that basically give us an analog input and convert those into a set of numbers that can then be processed inside the CPU. So we will talk more about analog signals later. For now, just be aware that GPIOs could potentially be analog as well. Now there are a few other sort of careabouts, as they say, right, for these circuits. One of them is, if I have a pin that is configured as an input, right, but I have not actually connected anything to it, what voltage am I going to see over here, right? And the bottom line is, from an electrical point of view, I cannot answer that question, right? I do not know what is connected at the input of this. I do not know whether it's 0, I do not know whether it's VDD, I do not know whether it's something in between, right? The point is that all that I can say is no current is flowing in here because there is no circuit. This point has been left unconnected. What we usually, the term that we use for it is, we say that it is a floating terminal, right? And when there is a terminal that's floating like this, in general you cannot say what the voltage on it is going to be, right? In most cases, the reason why something is floating is because this particular input also has a high input resistance or an input impedance, as we call it, right? The impedance also takes into account capacitive or inductive effects. So we usually refer to it as being a high impedance, and normally what we say is that a floating state, right, a floating input is considered to be in a high impedance state, basically saying that no current can flow in here, but that also means that I do not know what exactly this voltage is going to be. In some cases this may be alright and I can just deal with it and move on, but there may be cases where I do not want these kind of floating terminals. So instead what I could do is I could basically take a resistor, right, and connect it from this down to ground, okay. Now what that means is, if I have now still left this unconnected, it does not matter. The fact that there is a resistor over here means that this is going to get pulled down to ground, because if this voltage was anything other than 0, current would flow through this resistor until such time as this voltage gets pulled all the way down to 0, and then current stops flowing, okay. So it sort of makes sure that this voltage over here is at a safe value, a known value, more than anything else. I do not care whether it is 0 or whether it is VDD, I just need it to be known, I do not want it to be floating around randomly. So this is especially important in certain kinds of inputs where, let's say, I expect something to be connected here and I am sort of reading this input pin value into my CPU as a GPIO, assuming that it is connected, and based on whether I see a 0 or a 1, I want to actually do some kind of behavior, right. Now if this was left floating, it is quite possible that for some unknown reason that voltage temporarily goes high, causes this to become high, and in turn triggers some internal functionality that I did not want, right. By having a pull down resistor over here, it prevents this kind of false triggering. It ensures that unless there is actually an explicit connection out here, this voltage cannot go high. Now what happens if there is an actual connection which is trying to pull this up to VDD? That's fine. All that it means is some amount of current will also flow down through this path, but this voltage can still be taken sufficiently high that it would be seen as a high voltage by this input. Remember, the thresholds can come into play over there. I don't need to pull this all the way up to VDD, I just need to pull it above the threshold so that this sees it as a high voltage. I could alternatively use something called a pull-up resistor, right? And pull-up resistors are basically things which by default, if there was no connection out here, would pull this voltage up to VDD. If there was a connection that tries to pull it down, right, then that also works. What would happen in such a scenario is that I would then have some current flowing through this resistor and down to ground. This voltage would end up being fairly close to ground, right, although there would be some voltage drop across this resistor, and that's fine, that's good enough for this input to see it as a low voltage and input 0. Now where this becomes particularly useful is there are certain kinds of chips, sensors and so on, which are called open drain. In order to really understand this, you need to go into how MOS transistors work, so I'm going to sort of skip over that for the time being. I don't want to get into the details there. What is important to know is you can think of it as there is a switch out here. When that switch is closed, it will definitely pull this voltage down to 0. But when the switch is open, for whatever reason, right, maybe the sensor is inactive, this switch is unable to pull this down, right. What that means is this resistor will then take over and pull this voltage up to VDD, which is good. That's all that we really need. We have some way by which we can pull this up to VDD, and whenever this sensor is active, it will pull it down to ground. The interesting thing is you can go one step further and you can connect yet another block like this, right, and depending on which one of those is active, it can pull this down to ground, but if neither of them is active, automatically the result would be pulled up to VDD. So this kind of open drain connection basically allows us to connect multiple such devices in parallel at the same point, effectively creating some kind of a short circuit because we have connected all of them together at the same point, but without the problems of a short circuit because that pull-up resistor takes care of ensuring that only one of, if none of them are active, only then it will pull this up to VDD, and at any other point in time one of them would be able to pull the output down to 0. So open drain connections are used in interfacing certain kinds of sensors, and you will come across them at various points when you try to build embedded systems. The other scenario where this becomes useful is if something as simple as a push button, right. What does a push button do? It basically says if I press this button, it closes this contact and basically provides a path from this point to ground. In other words, it pulls this voltage down to 0. What happens when I release the button? It breaks this connection, right, and at that point I don't have, normally if I did not have this pull-up resistor, this voltage would then be floating, but by putting a pull-up resistor over there, I implicitly manage to make sure that whenever the push button is off, automatically this gets pulled up to VDD. So it simplifies my circuitry in that sense. Now keep in mind that if I did not have a resistor out here and just sort of connected this up as a wire, that's a problem, because what would happen is when I then press this push button, I would end up with a short circuit. So I do need to have a resistor, and in fact even the choice of how big that resistor is kind of important. Usually there are standard suggestions given by the data sheets or the manufacturers about how you can do this. More importantly, you can do this kind of pull-up just through a configuration setting inside a microcontroller. There are actually resistors present inside the chip that you can use as pull-up resistors if required. Now with all of this, what we have seen is that the way you program the GPIOs is by using something called the hardware abstraction layer, right. We don't want to actually get into the nitty-gritty of setting bits in registers at each point. that's how it works at the end of the day, but you don't want to keep doing the bit manipulation code again and again, highly prone to errors, right. More importantly, the bit manipulation is MCU specific. It's specific to the particular family and in fact the particular instance of the microcontroller unit that you are working with, right. There might be a microcontroller on which maybe the GPIO base address is different from a very similar other kind of microcontroller, or there might be one where a particular pin is actually connected on the 6th location rather than on the 5th location. Okay. Now, what the hardware abstraction layer allows you to do is, as we saw in the previous example, right, you can just create functions such as HAL toggle pin, and that would be sufficient to go and figure out which pin at which address needs to be toggled and how to go about toggling it. Now, if you switched over from an ARM microcontroller to a completely different family, let's say the ESP series, you probably will still have another HAL toggle pin function which does not use the set reset registers used in ARM, but achieves the same functionality of toggling the pin. So what that means is the code that you write in C now becomes portable. You can basically switch it over by just customizing a very limited set of files which provide the hardware abstraction layer for you. So in a lot of the programming that we will be looking at, the hardware abstraction layer is something that we will either implicitly assume or we will need in order to do anything non-trivial with it. An example of the HAL code is what we already looked at in the C code, right. You basically have a struct that allows you to define a GPIO. You can specify things like the mode, pull up, pull down, speed and the pin configuration, everything over here, and one function called HAL GPIO init will allow you to take care of the configuration details without having to worry about what parameter do I need to specify in order to make something pull up or an output versus an input, or what do I do if I don't want either pull up or pull down resistor to be active, because after all I am using this as an output port, right. And various such parameters just get abstracted away using these kind of hash defines or functions, and the level at which you can program reaches a higher degree of abstraction, which importantly makes it more portable.